This meeting is now being recorded.
Today we have with us Chantell Murphy from University of New Mexico, who's going to be talking to us about pyroprocessing and new safeguards approach. So Chantell.
Yes, okay, thank you. Thank you for inviting me to give this talk today. My PhD work is on developing a new safeguards approach for pyroprocessing facilities. This work was done in collaboration with my fellow graduate student, Phil Lafreniere at the University of New Mexico, as well as Dr. Michael Simpson's lab here at the University of Utah in Salt Lake City, where I currently am, finishing up my experiments in the metallurgy department. And I want to thank the impact team at Los Alamos National Laboratory. Today I'm going to start off giving kind of a very overview summary of my work. I'll go into the background and discuss some of the safeguards challenges. And I'll talk about my research and how I'm trying to address those challenges, and then talk about some of the conclusions. Big picture slide. The increased interest in pyroprocessing and related non-proliferation issues has led to efforts to develop a standard safeguards approach for international commercial pyroprocessing facilities. The safeguards approaches must meet the International Atomic Energy Agency's standards for detecting the diversion of significant quantities of nuclear material in a timely manner. This work presents a diversion scenario process model for a prototypical pyroprocessing plant's Electra Signer. As with most of these talks, we will begin with the description of the nuclear fuel cycle. The nuclear fuel cycle is a series of industrial processes that involve the production of electricity from uranium in nuclear power reactors. In the front end of the nuclear fuel cycle, nuclear material is processed for use in the nuclear reactor. In the back end of the nuclear fuel cycle, spent nuclear fuel is either stored or it's reprocessed for use in new nuclear fuel. My work obviously covers fuel reprocessing. And there are two processes used to recover uranium and transuranics. Those are the plutonium and extraction process, also known as PUREX, and the pyroprocess. These are referred to as wet and dry extraction, respectively. PUREX is the most commonly used in several countries, and it uses chemicals to separate plutonium and uranium. Pyroprocess facilities use electrochemical separation to recover uranium, while plutonium remains mixed with other actinides. Advocates of pyroprocessing say that that difference makes the process significantly less proliferation prone than PUREX. The IAEA's mission is to promote the peaceful use of nuclear energy while inhibiting nuclear energy's use for any military purpose, including nuclear weapons. And safeguards are used to help carry out that mission. Safeguards encompass a set of technical measures to verify that states are honoring their international legal obligations to use nuclear material and technology for only peaceful purposes. All right, I'm a little sick today. The main objective of international safeguards is the timely detection of diversion of significant quantities of nuclear material from peaceful nuclear activities. Nuclear material accountancy is employed by measuring quantities of material in defined areas and changes in those quantities within defined time periods. The inspectors use a variety of tools such as gamma detectors, neutron counters, and metallic seals with the goal of verifying that the amount of material declared at each facility is in fact there and accounted for, and that material unaccounted for does not exceed a significant quantity. And a significant quantity is defined as the approximate amount of nuclear material needed to manufacture a nuclear weapon. So in the case of plutonium, that amount is 8 kilograms. This can lead to complications safeguarding large, high-throughput facilities, such as reprocessing plants. For example, the Reprocessing Plant in Japan processes approximately 8,000 kilograms of plutonium per year. This would require a mass balance uncertainty of less than 0.1% to meet IAEA safeguards requirements of detecting 8 kilograms. As you can imagine, high-throughput facilities pose particular problems for traditional IAEA safeguards. So let's begin with how pyroprocessing works. While there are different pyroprocess flowcharts, let's walk through the general unit operation. First, spent nuclear fuel enters the facility as either an oxide or metal. Most fuel enters the facility in oxide form, and it is first converted into a metal through the oxide reduction unit operation. Then the metal fuel is processed in the Electra Signer, which produces 3 separation streams, one for uranium, one for granite, one for the noble metal. Uranium is cleaned and processed into metal ingots for use in new fuel assemblies. The transuranics are recovered and put into ceramic waste form, and the noble metals and cladding are processed metal waste. All 3 operations transfer clean salt back into the Electra refiner. So strict nuclear material accountancy is difficult to do with low uncertainties in high throughput facilities. And it is made even more difficult in pyroprocessing facilities. Pyroprocessing facilities pose these problems as you saw in the flow chart. Spent fuel is put into the facility and immediately reduced into metal. And unlike at Purex facilities, there is no input accountability. All of the spent fuel is dissolved and can be accounted for, and samples can be taken. So it's difficult to know exactly what is going into the facility from the very beginning. Pyroprocessing facilities require steady state operation at very high temperatures. So periodic plant flushouts are not, they're just not economically feasible. And due to the closed dynamic nature of the process, sampling methods cannot meet required levels of confidence. And the Electra Signer in particular is of safeguard significance because plutonium can be electrochemically separated from other actinides. So how is this done? Here is a diagram of a typical electrochemical cell. Electrochemical deposition, or electrodeposition, is also known as electroplating. It's a very common process of depositing material onto a conducting surface from a solution containing ionic species, the salts. This fabrication technique is commonly used to apply thin films of material to the surface of an object to change its external properties, such as to increase corrosion protection. A typical setup for small-scale electrodeposition is shown in this figure. It consists of 3 electrodes, the anode, the reference electrode, and the cathode. The electrodes are connected to a potentiostat, which is the instrument that controls the deposition process. The electrodes sit within a vessel containing an electrolyte that has ionic species dissolved in it, such as the U3 ion. And in the electrolyte is the uranium fluoride. The cathode, which is a tungsten rod, in my case, is the object that will be plated, as you can see here. These are the deposits. The anode is used to complete the electronic circuit and provides metal for oxidation. And the reference electrode is used as a fixed reference point for the potentiostat. An electric field is applied across the cathode in a way as to give electrons to the ions in solution so that they form uncharged elements or compounds that would prefer to adhere to the surface of the cathode rather than remain dissolved in the solution. The strength of the electric field or the potential is measured versus the reference electrode, but the actual current is flowing between the cathode and the anode. Your normal operating conditions in the Electra Signer, uranium is electrodeposited on the cathode through reduction. You're reducing the uranium ions in the solution to form uranium metal onto the cathode. Under off-normal operating conditions, plutonium is deposited onto the cathode, co-deposited. Now, several off-normal scenarios have been identified that lead to plutonium co-depositing on the cathode. These include poorly characterized anodic feedstock, a change in electrode submersion depth, which changes the surface area of the cathode, change in electrode rotational speed, changes in temperature, and changes in electrolyte concentration. Now, my work focuses on changes in electrolyte concentration. And so how do we deal with this problem? How do we track plutonium in this system when we're dealing with off-normal operations? One of the proposed solutions is this concept of signature-based safeguards, which is being developed with the University of New Mexico and the University of Utah. And the main goal is to obtain real-time or near real-time detection of anomalous events through the complementary use of traditional nuclear material accountancy and process monitoring techniques. It has been suggested that Curium will track plutonium through the pyroprocessing system, enabling non-destructive assaying of plutonium by counting neutrons from Curium-244. If plutonium and Curium behave the same electrochemically, then counting neutrons could be used to estimate plutonium concentration. But perhaps electrochemical processing techniques could be used to help corroborate this theory and achieve a more real-time assessment of the materials in the process. Some of the techniques I'm looking at are cyclic voltammetry, chronoamperometry, normal pulse voltammetry, and so I've shown some graphs here of the CV and CA that I've run. Cyclic voltammetry is an electrochemical technique that can be applied to study all electrochemical reactions. It is used to collect information about the type of reactions observed in the system and the potentials at which they occur. It measures the current flowing through the working electrode as it cycles through a range of potentials. In chronoamperometry, or CA, the current is measured versus time as a response to a constant potential pulse. And the recorded current can be analyzed, and its nature can be identified from the variations of time. The response of these techniques is highly dependent upon the reactions taking place at that cathode, the working electrode. And so if diversion signatures are being benchmarked using these techniques, then they could be quite useful for quickly identifying diversion scenarios in the future. My work explores the key assumptions behind the neutron balance method in this context. Will the plutonium-curium ratio remain constant in the anode, in the electrolyte, and at the cathode? And if plutonium co-deposits, will curium follow it? And if it does follow it, will it be at the same ratio as it is in the salt and at the anode? Examining these assumptions in simulations and experiments help build the overall SPS model by providing diversion scenario signatures for a variety of off-normal events to help identify early their safeguard significance. Simulations for the Electra Signer are being carried out with a one-dimensional electrochemical transport code called ERAD, or Enhanced Resin with Anodic Dissolution. ERAD computes the output, the current densities, electrode potentials, and concentrations of elements at various locations in the system. The ERAD simulations were done for a simulated the Korean Advanced Pyroprocessing Facility under an operating cycle of 20 days. And it showed that plutonium can be separated from curium. So in this graph, the blue line shows the amount of plutonium deposited at the cathode. I've lost some information here on the graph. So plutonium was deposited, about 80 grams of plutonium after 20 days of operating, but curium did not deposit with it. So, but how do we know if ERAD is providing useful results? And how can we extrapolate that?
Just to be clear, the blue line here is the plutonium and the green is the curium.
Yes. My legend capture that. Blue line is plutonium. Green line is at 0, it's at curium. And so one of the questions is obviously, how do we know if ERAD is useful for extrapolating real-world events, real-world diversion scenarios? And so what we want to do is try to validate ERAD with small-scale experiments to see if the results are the same or similar. Unfortunately, plutonium and curium is not readily available for experimental use. So I use surrogates. The electrochemical parameters of interest were the valence state of the ion undergoing reaction and the reduction potential difference of the two elements. Literature review led me to terbium and gadolinium. Valence state of the reactions match, and the reduction potential differences are pretty close. The percent difference of 6 versus 4 is okay. I think I can make the argument that because the percent difference is larger in my experiment setup, and that if co-deposition occurs, if gadolinium does end up following terbium, and it's easier to make the case that co-deposition could occur with plutonium and curium, because their potentials are even closer. So I began with doing ERAD simulations of my experimental test plan. I did 8 rounds with a different ratio of terbium to gadolinium. And so these are the results from using 1 weight % of terbium in the electrolyte and then changes in gadolinium concentration for each round. And through all 8 rounds, 80 milligrams of terbium deposited on the cathode, and it wasn't until the ratio was about 1 to 1 where gadolinium started to co-deposit as well at about 20 milligrams. So those are my ERAD simulations, and I want to see if my experiments will also result in similar results. Here's a picture of the 3 electrode setup I have in the furnace, where I'm using a 5 mole % silver chloride reference electrode. All of the potentials are in reference to that reference electrode. The anode consists of a 6.35 millimeter diameter terbium rod, and the cathode is a 2 millimeter tungsten rod. The experiments, storage, and handling of all chemicals are carried out in a glove box with an inert argon atmosphere. The goal is to operate the cell to deposit terbium on the cathode. And so I ran 8 different experiments, as you saw from the previous chart, increasing the amount of gadolinium in order to see if that would also reduce. The first step was to take CV measurements of a mixture of just terbium. So I used a 1 weight % terbium in a crucible with lithium chloride, potassium chloride, eutectic salt, the total of 50 grams. And this is the CV that resulted from that in order to see where my reduction potential starts for terbium. I did the same thing with a mixture of only gadolinium. And then the experiments themselves were obviously a mixture of terbium and gadolinium. It was expected in the 2-component system there would be 2 reduction peaks, but there's only 1, and so that was an interesting result. This suggests that in an even larger Electra Signer unit, CV might not be immediately useful for getting real-time data on plutonium in the system. But the CV was useful in order to set the constant potential. And so if I had an overlapping view of these, you would see that at minus 2.13 volts, there was a current response. It began, there was a current response for the reduction of terbium, and there was not one for gadolinium. And so while the potentials are very close, minus 2.13 was a good potential at which to set my chronoamperometry runs in order to deposit terbium onto the cathode. So I did that. And these pictures are of the metal deposits from those runs. So as I said, I set the potential at minus 2.13 volts. I set it to approximately deposit about 2 milligrams of material. So I ran it for about an hour and a half or so in order to reach a charge of 365 coulombs. So these are some of the best looking deposits, I would say, that I was able to get. But the first picture is from the round 8, the run number 8, which is the 1-to-1 ratio. And then this deposit is from another set of experiments with a 100-to-1 ratio. So both of these were dissolved in a nitric acid, 20 milliliters. and I will run ICP atomic emission spectroscopy on them, hopefully later today, and I will figure out exactly what I got. Hopefully, well, probably going to be terbium, but maybe also gadolinium. The main goal, the main goal of combining and correlating this data from other sources is to see if you can get the real-time or near real-time information about how much plutonium is in any given process. That said, one of the problems with SBS and adding more sensors to a system is the introduction of more error. I am now fully prepared to accept the outcome where the error propagation does not increase confidence, and the answer might not actually be add more sensors to the system. And if this uncertainty pushes the boundaries into the significant quantity range, then that's still a very useful result, and it is certainly the next phase of data analysis for this work. But for now we're working under the assumption that signature-based safeguards is a powerful technique for safeguarding future power processing facilities. This work presents both a simulated and experimental diversion scenario, presents ways to identify associated signatures, and it will use nuclear material accountancy and process monitoring tools to detect those signatures. In the grand scheme of things, in a commercial power processing facility, the SBS system would hopefully be used to trigger early alarms or directed inspection efforts, which will in the long run save time and money for these very high throughput facilities. And we have so much time for questions.
Okay. Thank you very much. I wanted to start off the question. Can you go back to the figure where you showed the CV curves? I want to understand those a little bit better.
Sure.
I think it was 28. Yeah. So what's the vertical axis in this case?
Oh, I don't have it labeled. That is horrible. The vertical axis is current, so I'm looking at current versus potential. So the CV works by cycling the potential. You're stepping through a series of potentials. So you're pulsing the potential between, let's say, 0 volts and, in this case, about minus 2.5 volts. And then at each potential, you're measuring the current that's registered there. And so as oxidation and reduction reactions occur, the current changes depending on the species in the electrolyte and what is reacting at the cathode. And
so as you...
oh, sorry.
Yeah, go ahead.
In other papers, a lot of uranium papers, a lot of people do co-deposition of uranium and magnesium, but the CVs end up, you can see multiple peaks because presumably the reduction potentials are far enough apart that each individual element can be captured in the CV. But that's not the case here.
And so the reason you picked the minus 2.13 is that you see that there's a significant dip in the blue curve before the green curve starts to play out.
Right, exactly.
Okay. Okay.
So in theory, that potential should preferentially only deposit terbium onto the cathode.
Mm-hmm. Mm-hmm. Okay. Let's see. Ed had a question. Ed, do you have a way to ask it here? Are you?
Just the what I wrote.
Yeah. Can you go ahead and? Yeah. Can you go ahead and just ask it as a question for the
Sure.
maybe easier here?
Right. So there's a more fundamental issue with using curium as a surrogate, and that's the ability to determine the ratio in the input, because you can't measure it in the pyroprocessing cell. You have to use depletion codes, and those have an uncertainty which might overwhelm the other uncertainties in the measurements. So have you studied how the initial uncertainties in the calculated ratio would propagate into the SEID?
I'm just reading the actual question right now. Yes, that's kind of what I was getting at in beginning into the conclusion and data analysis part, is that error propagation through not just the initial fuel composition, which is certainly a significant one, which might be mitigated by doing a destructive analysis at some point in the process. But that propagation of uncertainty through not from the beginning of when you put the fuel into the process, and then processing it at multiple times, and trying to correlate all of these different sensors, I'm starting to understand better how uncertainty can really be increased through all of these different ways. And yes, I'm considering it, and yes, I am trying to figure out how to incorporate that into a usable, result.
Okay. While this figure is up here, I'm gonna jump to Matt Bunn, who had a question about the slide.
So Chantell, thanks. I'm wondering, in this slide, as you noted, you don't end up with two separate peaks when the two materials are mixed together. You end up with one peak, but it's also interesting that it's shifted over to the right compared to either of the materials by themselves. Do you have an explanation for that?
Yeah, it is. I don't have an explanation for that actually at the moment.
Okay.
But perhaps, perhaps there could be some useful information as far as kind of figuring out what caused the shift, and then how you can extrapolate that into figuring out what the elements are and what's happening with them in the system. I can only imagine that in a very large system, in the actual ER operating unit operation at the commercial facility, I imagine it would be difficult to actually see any individual peaks because you have, all of the elements essentially in your salt. So I guess I'm personally not entirely sure as far as using CV for process monitoring. I'm not sure how much use it could be for detecting individual elements.
Okay. Caitlin had a question. She says she doesn't have a microphone. She says, can you discuss more in detail the pros and cons of using surrogates here? And what about your particular pair of surrogates? Were there others you considered?
I mean, ideally, I would use plutonium and curium, but that's just, radioactivity, cost, availability, really not an option. I think so. Other surrogates were certainly thought about, and I have run other experiments using magnesium, terbium, gadolinium, neodymium. A lot of it came down to availability. Terbium was interesting because there's actually not a whole lot of electrochemical experiments done with terbium, and so it's kind of just from research and academic point of view, it was kind of an interesting element to use. And its reduction potential in literature was relatively close to plutonium, and that was maybe the main element that I was looking to use. And then from there, gadolinium was the next closest potential to match that potential difference between plutonium and curium. And so, yeah, those are kind of the main reasons. And magnesium, I think, which just had a pretty positive. Magnesium is usually a surrogate for uranium. The potentials are pretty close there. And magnesium, the valence states it's a magnesium 2, magnesium 0, so the valence states don't match, and it's a much lighter element. So I think due to the valence states, its potentials, the atomic weight, terbium and gadolinium were pretty good matches.
So, Caitlin, you may have seen her follow-up here. She said the main question is, does it matter so much that these two elements typically only have +3, +2 oxidation states, unlike plutonium, which has several?
The reaction we're interested in is this the redox couple of 3, plutonium 3, plutonium 0. So those are the reactions we're looking at. I would say no.
Okay. Matthew McKinsey.
Hi. Can you hear me okay?
Yes.
Yes.
Oh, great. Chantell, thank you so much for your presentation. I work at the Natural Resources Defense Council, NRDC, and someone who's been part of the UCF Summer Symposium and part of this community is Jungmin Kang, who worked here at NRDC up until January 2nd. One special research interest of his was proliferation issues around pyroprocessing. And of course, that's an especially pertinent issue for South Korea. Jungmin was appointed as the chairman of South Korea's Nuclear Safety and Security Commission on January 2nd. It's quite astonishing. So he's in charge of nuclear safety and in charge of a lot of nonproliferation policy for South Korea as well. So I didn't know if you were aware of that. I'll put a link in here to the website of South Korea's. It's like their NRC, but I think with some functions of state rolled in terms of non-proliferation. So if you're Chung Min, he was on the last of these webinars. In fact, he'll be at the NRC's Regulatory Information Conference, the RIC, this March 13th through 15th. I don't know if you were going to attend, but he's very engaged on the issue of proliferation and pyroprocessing. So my question is, and some of your presentation addressed this, but I was wondering if you might turn to a different perspective on pyroprocessing and proliferation. The presentation, largely talked about a scenario where pyroprocessing may be used as part of an energy, part of the energy sector, but may be diverted. What is the perspective of a country that from the start wants to develop nuclear weapons? Would pyroprocessing at all be a route that country would go? And I was wondering if there are any technical insights into that question.
If a country wanted to proliferate,
if that was the objective from the start, would pyroprocessing, would you consider that as a leading option, or would it make more obvious sense to lead with a Purex approach or something else?
If you just had all of the resources and all of the money, I would imagine that a reprocessing period would not necessarily be the most attractive option, because you do have to deal with spent fuel. And if you have an easier way to access uranium or plutonium, well, I guess enrichment would be really quite ideal, but if you have
I think the question really is, if you were going to do this, are there advantages of Purex over pyroprocessing that might cause you to choose one over the other?
I think maybe the same arguments that are said, about Purex, and that it's kind of messy, and very large. Maybe the pyroprocess would be attractive, but you still have to deal with co-deposition, and then you have to separate out the plutonium. There's like a couple more steps involved.
Mm-hmm.
Okay, thank you.
Yeah.
Matt Bunn, you're next on the list here. You had another question.
So I was just wondering, perhaps I wasn't listening closely enough, but I'm wondering if you could summarize the overall safeguards approach that you're advocating here. What is the relative role of the neutron monitoring, the CV, and another monitoring in the system? At one point in the discussion, you said CV might not be able to see particular elements in the mix of nasty stuff that's actually going to be dissolved in the salt in a commercial system. Does that mean that CV maybe isn't so promising for safeguards?
It might, right, exactly. It might be that. So the initial investigation was to look at these variety of electrochemical techniques and to see if any useful information can be gained when playing out these diversion scenarios, to see what signatures are there. And so a lot of the other students have typically been using doing uranium, plutonium studies. And CV in those cases did produce two distinct peaks. from which you can, do a variety of analysis on to perhaps determine concentration in the electrolyte. But so my research ended up with something a little bit different. And so maybe in the case of plutonium and curium, CV won't necessarily be useful, but that's okay. Maybe it's better to kind of start ruling out potential sensors and measurements as opposed to adding more to the system. So these, essentially the main idea is to use these electrochemical methods as a way to complement other traditional NMA methods, which, typically have to be done during the physical inspections, which are done periodically. And for these large throughput facilities, ideally, they would want some type of, just kind of online monitoring system that could just use anomalous events, that are outside of normal operation, that are not just, not just anomalies, but also significant, significant anomalies. And so maybe if there's a way to capture boundary conditions from normal operation versus off-normal that leads to a safeguard significant event, then, maybe that could help make a more efficient safeguard system for these large throughput facilities. So that's kind of the underlying operating assumption behind the SDS model. And then so now we're kind of just doing the experiments and simulations to see, if that could be done. And so I'm trying to figure that out.
Okay. Rob Goldston, you had a question.
Yeah, I've got a really simple question. That plot of current versus voltage has both signs of current for a given voltage. Is that because of the rapid sweep, or, how is it you get two currents for a given voltage?
I couldn't really quite hear the question, but you said, how is it that you get two different currents of
So
opposite?
if you go back to I think slide 28 that had the plots on we were looking at, the CV plot.
Yes.
Yeah, the question is, it looks like
Well, I'm a plasma physicist, and I'm used to sweeping voltages, but for each voltage I only get one current. So how is it that you get, what's going on here? Is this a time-dependent case? Is that the key point? 300 millivolts per second, is that key?
The 300 millivolts per second, the scan rate.
Would you get very different answers if you scanned at 1,000 millivolts or 1 millivolt?
Yes, the scan rate, right, exactly. The current changes, the current response changes depending on the scan rate.
And have you looked to see if you do a slower scan? And so there's real strong hysteresis here. The current is changing sign for a given voltage when you come back to it often. If you went to minus 2.5 and back to 2.
This is capturing the reduction and oxidation peaks. And so I start with a more positive potential, and then I move it more negative. And then as I move it negative, the reduction reaction occurs. And so for this particular graph, can you see my little cursor?
Yeah, I see the pointer.
So the reason, so what you're looking at here is the forward, I guess like the initial sweep, reducing the current, and then at around minus 2.12 volts, you start to reduce terbium onto the cathode until it reaches its reduction peak, and then it continues to cycle, and you could reduce more elements But then when you reverse the potential, it comes back, and now you're seeing the oxidation peak. So at that cathode, now the terbium is being oxidized back into the electrolyte solution. And so that's why the current is now positive. And so these aren't taking place at the same time. It's cycling. So it's
yeah, obviously they're not at the same time. But I'm a little struggling with the physics of what's going on. In any event, one, you know, from a practical point of view, one might ask, could you get better distinction if you swept more slowly so that everything is essentially in quasi-equilibrium at each moment? And then one could take that upper right-hand curve and vary the ratio and see if you could see big changes in the structure of the curve. Might be more obvious with a slower speed is what I'm suggesting.
Right. Perhaps. I think that my slower scan rate curves ended up looking uglier.
Sometimes ugly is good.
Yeah, maybe.
I don't know. I'm just, as a physicist, I'm just sort of interested in what's going on. But that's because you might want to dig a little more into what's physically going on and whether there's a way to get at what you want by keeping everything scan rate, looking at the ugly patterns, whatever. That's all.
Okay. Yeah.
Ed, did you want to come back in and mention your discussion, the point you were discussing here in the comment?
I was just responding to Matt. So, you know, I don't think the issue is which is better, but the concern has always been that if pyroprocessing is painted as something which is more proliferation resistant than Purex, and that helps it to avoid some of the restraints that that are currently the constraints that are currently applied to conventional reprocessing. But it's just not true that it's really any more proliferation resistant, so that could be a problem. The U.S. determined back in the GNF era that pyroprocessing actually should be considered reprocessing, but that message hasn't really gotten out to a lot of the community.
So any other questions or comments for Chantell?
Can you hear me?
Yes.
David? Maybe there's an interesting distinction here between two different kinds pardon me, of proliferation. A breakout kind of proliferation where I think we all agree that you set this all up, you just play with the electrodes and you can get surf plutonium. And so breakout is a real risk. But maybe it's possible to keep track of diversion or slow misuse with some of these technologies. So, you know, maybe you could detect the breakout, but, you know, it would be too late. But if you can detect it, that's at least something. Even if you can detect small misuse, that's something.
I couldn't quite hear all of that. Sorry.
Rob, I think Rob was saying that there may be two different issues here. One is breaking out. One is sort of building a process that would give you the ability to produce material, and the other one is can you figure out monitoring that would allow you, in principle, to have an ongoing process and detect any diversion from an ongoing process, and that those I think that's basically it. Is that what you're saying, Rob? That those may be different,
right?
Different problems you're trying to solve.
It may be the case that you can't fix the breakout problem, but maybe you can at least detect misuse with technology.
Right. Yes, I agree, and I think that the idea, well, at least with combining the process monitoring along with the targeted nuclear material accountancy methods, I mean, it's probably most helpful for the long-term operation monitoring, or maybe the protracted, kind of small diversions here and there, and then adding that up.
Okay. We're just about at 1 o'clock here, so I think I'll call us to a close here. We'll all be waiting to hear what happens when you dissolve the material in your cathode and see what you get on that. So good luck with that. So thanks very much for giving us this talk today, and thanks people for joining us.
Yeah, thank you everyone.
Thank you. Cheers.